Okay, so the last question of the worksheet is this Javelin competition. And so you'll see here that we get given the distance or the horizontal displacement that Klaus throws the javelin. We're really after what Gary throws, the horizontal displacement, and then you can compare it to see if he beat Klaus. And so we know that Gary threw at 44 degrees with a resultant velocity of 29 meters per second, and he released the javelin at 1.9 meters above the ground. So I might draw out the initial velocity there, and the resultant is 29 meters per second. And we know that that was at 44 degrees and at 1.9 meters above the ground. I might also draw out, if we have 1.9 here, so this is the initial velocity, but remember that's going to change over time, and so whilst it might have been thrown at that angle, we might have, well, we might do is find that it ends up going and hitting the ground here. Now this is obviously a horrendous drawing here, but this gives you an idea of what's actually happening, and this is the initial velocity of it. And so how are we going to find how far it goes? Well, the horizontal displacement is equal to the horizontal velocity multiplied by time in the air, and that's the total time, so going up and down. And so how are we going to find out horizontal velocity and time? Well, we start with the components of this horizontal velocity vector. We can, this resultant velocity vector, and so we can break up, or straight away get the horizontal velocity. And for that, we'd use the law of cosines. So, sorry, not law of cosines, the SOHCAHTOA, but the cosine aspect of that. So adjacent divided by hypotenuse is the cosine of the angle, or specifically cosine of 44 equals horizontal velocity here. I'm just going to abbreviate that with a HV, is divided by 29 meters per second. And so the horizontal velocity is going to be equal to 20.86, and we can put that up here, 20.86. Now obviously the vertical velocity is going to be very similar to that because this is close to 45, but it's not exactly 45, so it's slightly different, and we're going to need this vertical velocity to get time in the air. And so we already have this ticked off, which is fantastic, horizontal velocity, but to get vertical velocity we're going to use SOHCAHTOA, but in particular sine of an angle equals opposite over hypotenuse, which means in this case sine of 44 equals vertical velocity divided by 29, and we can work that out to have vertical velocity equaling 20.145. Okay, so we can use some of the ways or the procedure that we've done in previous examples to get our time up fairly easily, but then it's going to be an extra step getting time down. So time up we can calculate using the laws of constant acceleration, and in particular the first law of constant acceleration, which is final velocity equals initial velocity add acceleration multiplied by time. And so I won't write that out this time, but I'm going to put in the values for it. So final velocity is 0 going upwards. The initial velocity going up is 20.145. The acceleration is 9.81, and we've got multiplied by time there. So we work out the algebra, and time up is going to be equal to 2.05 seconds. So time up 2.05 seconds. Now we have horizontal velocity and we have some of the time up, but what we need is total time, so time up and what is going to be a difference in time down obviously larger there. So how do we get time down? Well, we need to figure out displacement up to add that to the 1.9, and this is definitely out of scale because this is going to end up being much larger, but we're going to add this to 1.9, and then we're going to be able to use that displacement down to get total time down. Okay, so if we say if we use the second law of constant acceleration to get displacement up, which is the initial velocity equals, the final velocity equals the initial velocity squared, add 2 times acceleration times displacement. We can substitute that in as 0, which is final velocity going up, equals 20.145, which is the initial velocity going up, and we can square that, add it to 2 multiplied by 9, or negative 9.81, multiplied by displacement up. Okay, then we rearrange that formula, or we solve for the algebra and displacement up. So this section in here is going to equal 20.68. So as you can see, that's much larger than this, so it's really out of scale here, this particular drawing. But you can imagine that that's 20.68 meters, that's 1.98, so the displacement down is going to be equal to 20.68 add 1.9, which is going then to be equal to 22.58. So now we have our displacement down, we can get our time down. Remember, we need to add time up and time down together, and then we've got our last part of our formula there. So we're going to use then the second law of constant acceleration again to get time down using our displacement. So in particular, the 22.58, which is displacement. Displacement is equal to initial velocity, which in this case is 0, squared, add half, so 0.5 multiplied by negative 9.81 time down squared. And so that is going to be equaling 2.14 seconds. And then we have our time down, we have our time up. So total time is going to be equal to 2.05 add 2.14, which is 4.14, and our horizontal displacement is then going to be equal to horizontal velocity multiplied by time, horizontal velocity being 2.86, total time being 4.19, and therefore our final answer being 87.40. So if Gary ended up throwing the javelin 87.4 meters and Klaus ended up throwing it 83.83, then Gary is our winner.